Right, everybody, welcome to 3 Deviations again. My name is Stuart Christensen. We'll be doing surface area today. Now, in the past couple of videos, we looked at the idea of applications of double integrals. So how could we use double integrals to look at real-world problems? So we looked at surface density for charges and for masses. We also looked at moments, masses, and we looked at the moment of inertia in the last video. Well, today we want to look at one last application. This is kind of analogous to something we did in single variable, but we will be looking at surface area. But today I just want to derive the formula for it because there is a little bit of a sleight of hand. Now, in single variable calculus, if you remember, if I had a function like this, I could find its arc length. Now, finding its arc length was something entirely different than finding the area under the curve. What I could do is I could take little pieces, I could take this and a hypotenuse to find the area under the curve. What we ended up getting, if I wanted to find the arc length, and I kept doing this for each little bit, adding all of those hypotenuses up, would get the integral over whatever kind of section, let's call that section S, I wanted to. So if this was, let's say if this was section S, if I wanted to find the arc length between here and here, on the section S, take the integral on the bounds, the square root of 1 plus y prime squared dx. If I took that integral, I could find the arc length. Now we're going to do the same kind of thing, but instead of finding the arc length, we're going to find the area of a surface. So it's kind of similar to the arc length, but it's a 2D analog. Now the derivation starts with taking the limit of a sum. Now let's actually go over what I'm doing here. Now I have my xy plane here. I have some surface there. What I will be doing is, instead of adding up tons of little areas, I'll be adding up tons of little surfaces up here. So I'll be taking the tangent surface to the plane at some, so we call this a little delta of a tangent surface, so it's tangent to the plane, delta Tij for the ith x point and the jth y point, and that is associated with some little area a sub ij, right? Okay, now I'm hoping this makes sense so far. Anyways, we take the limit, so we take Tij to be as small as possible, and we sum it. And first need to define what Tij is. Well, from our vector analysis unit, kind of where we introduced vectors and talked about vectors, we determined that to find the tangent plane, or to find delta Tij, the area there of a parallelogram, because Tij would be a parallelogram, we take the magnitude of A cross B, okay? Now, we need to define A and B. Now, A, in the ith direction, is going to be defined by delta x. And then in the kth direction, it's going to be defined by the derivative of x, the derivative with respect to x at x sub I, y sub j, delta x. So then we also need to define B, which is delta y j hat plus partial y at x sub I, y sub j, delta y times k hat. And then we need to take their cross products, which is the determinant of a matrix. So we take A cross B. You could really do this with the, well, might not want to do it with the sine of theta, cosine theta definition. It's going to be easier this way. Take the matrix ijk, delta x, 0, partial x, 0, delta y, partial y. What we get here is we get negative partial x at x sub I, y sub j, I hat, minus partial y, x sub I, y sub j, j hat, plus k hat, delta A. Now, if I want to take the magnitude of this, I square all the components, add them together, and square root it, I get delta Tij is equal to partial x squared plus partial y squared plus 1. Now this looks very similar to what we have in our arc length case, because what we had 1 plus partial f, or these are normal derivatives, but I'm putting it as a partial, I don't know why, squared. And we took the integral of that. Now, this looks very familiar, because we have our y component and our x component, but we're adding another component, so obviously we need to take partial derivatives. We square them, we add 1 for our z component. Of course, we have the delta A. It's our quote-unquote differential for now. It's an actual area in the Riemann sum. But we need to take the limit now. So if A, the surface area, is defined as the limit of the sum of delta Tij, then that means that it's also equal to the integral over the domain, whatever domain I want to find the surface area under. If I have a domain like this, and that's mapped to some surface area like this, then I want to find this surface area over this domain, which is hopefully parameterized either polarly or rectangularly. So I take the integral over the domain of the square root of 1 plus partial f partial x squared plus partial f partial y squared, all with respect to an area element. Now, that is how you would find the surface area. So you need to find a lot of things. Now, what I would recommend doing is you kind of have 3 steps, right? You have 3 steps. The first step is to determine boundary. Sorry if I spelled that wrong. The second step is you need to find your derivatives. The third step is to perform your integral. Is it perform or preform? I'm not sure. Perform integrals. And that will give you your surface area. Okay, so that is how you do that. Another thing, I know a lot of people might gripe about this, but sometimes it's easier to do your integral notation a different way, which might kind of save you some time writing it. I don't think it does personally, but if you need a lot of integrals, then it might. Just a quick thing on notation. If I want to write the double integral over the domain of f of x and y dx dy, that's equivalent to writing the integral over the domain, one integral, it's just assumed, of f of x and y d squared x. Now, some people like this notation just because it's a lot easier to remember, or it's a lot easier to write down. It's a lot faster, especially when you get more than 2 integrals. Also, it kind of is a more advanced notation because it says you can put it into polar, you can put it into rectangular, whatever you like. This 2 here just means it's a double integral, so it's a 2-dimensional integral. So that means you can do it in polar, you can do it in rectangular. That's all I've got for today's video, a little bit on notation and a little bit on a derivation. In the next video, I would like to cover some examples for these surface area examples, surface area integrals. And then after that, I would like to introduce triple integrals, and we're going to be spending the rest of the unit talking about that and the Jacobian matrix. Thanks for watching. We'll see you in the next one.